Okay, so yesterday we have seen the introduction part, and next we have seen what is scalar and what is vector. And today we also started with a vector representation. A vector is represented graphically as a line segment, and this part is equal to a magnitude of that, and this we represent like a tail and this as head, and the direction of the vector is represented by an arrow mark. Okay, so the next point is what is equal vector. So two vectors are said to be equal if they have same magnitude and same direction, as it has been shown that A and B has same magnitude and they have the same direction. Okay, so next part is what is unit vector. So this is very important. A vector of a unit magnitude is called as unit vector. Say for example, I have a vector A here, and for this vector A, I need to define unit vector. So what I do is, I write it as mathematically that vector A divided by its magnitude. A unit vector along A is defined as a vector whose magnitude is unity and its direction is along A, that is, and we represent a unit vector with a cap. Okay, that is small a, and I'm trying to define a unit vector along A vector, so it is being written as subscript small a subscript capital A with a cap. This represents a unit vector along vector A. So please remember this convention. This is what we are going to follow in all throughout the course. Okay, and which is given by a vector A divided by the magnitude of magnitude of vector A. Okay, and we should know that the magnitude of a unit vector is obviously 1, and it is a dimensionless quantity. Okay, so now you could see that this particular vector A, I can write it as, and in fact we can write any vector as A, that is a magnitude, multiplied by a unit vector. And you could see it is completely defined because this part represents magnitude of that vector A, and this part is taking care of the direction of the vector. And you could see the magnitude is not disturbed because the magnitude of this vector, unit vector, is 1. So is this point is clear about equal vector and unit vector?
Yes, sir.
Yes, is that clear?
Yes, sir.
Okay.
Yes, sir.
Yeah, if you have any doubts, so we can resolve that and we can proceed to the next thing. Usually this particular point is very important. I mean, like many students think that unit vector is something defined isolatedly. It is nothing like that. For a given vector, we can define the unit vector. That should be very clear. Is that clear? Okay. So the next part is vector operations. So we'll try to see how do we perform vector addition. And I hope, you are all familiar with this. We'll have a just quick review. Okay. So for example, I have two vector A and B represented here. And now I want to add these two vectors. So what we do is, we follow this simple method. To add two vectors A and B, we draw two representative vectors A and B such that the initial point, that is called as a tail of B, okay, coincides with the final point tip of A. That is, we try to, what we say is, slide this particular B vector such that the tail of this B vector coincides with the head of A vector. That is what is being shown here. Okay, and before this, I want to tell one more point. That is, vector has both magnitude and direction, but it does not have the position. Okay, and because of that, we are really free to move this vector B, provided that you don't change its direction or the orientation. That is, you can move this vector B such a way that still you are parallel. Okay, you can move like right, left, up and down, but you should take care that you should not disturb its direction. So in that way, we try to move this vector B such that the tail of vector B coincides with the head of vector A. That is what is being shown here. And now what we say is you join a point from tail of A to the head of the B. And this green line, what I'm trying to show with the dotted line, represents a sum of two vectors A and B, that is C vectors. Sum of two vector is back again a vector which is we denoted by as a C vector. And you could see something interesting that I can complete this diagram as a parallelogram. That is, I draw one more parallel to this B, which I have shown as a dotted line. And I can draw one more parallel to this A, which I have shown as a dotted line. And now you could see when I draw these two lines, it completes the parallelogram. And this represents a diagonal of the parallelogram. Now you could see from this figure, I have tried to add A plus B, so I got this sum. And if I try to follow the same procedure what is mentioned above, that is, I can add B plus A, and you could see that I get the same result. Okay, and hence I say that from above figure it is evident that vector addition is independent of the order in which the vectors are added. That is, they are commutative. That is, you can add A plus B or B plus A. Okay, it can be also show that vector also obeys associative law of addition. If you have three vectors, you can if you have three vectors, you can add in any order. First you can add B plus C and then you can add with A, or first you can add A plus B and then you can add it with the C. Okay, so is that this point is clear? How do we add two vectors graphically?
Yes, sir.
Yes, sir.
I hope you are all aware of this, right? From Q2.
Yes, sir.
Yeah. We have some. We have many different names like parallelogram law of addition. Or we can use it as a head-tail method also. Okay. But this procedure is also useful when we proceed towards this course. Okay. So next point is how we can perform vector subtraction. So that is quite simple. This A minus B, I can write it as A plus in a bracket of minus B. Okay. So now if B is a vector, then minus B is also a vector with the same magnitude as B, but in the opposite direction. So what we can do is even subtraction can be performed as an addition, provided we add A with the minus B vector. Okay, so here I have again two vectors A and B, and I need to perform subtraction of these two vectors. So what I can do is again the same procedure as I told you, that you try to slide this vector B such a way that you don't disturb its direction, and bring and coincide it to the the tail of the B should coincide with the head of the A. That is what we have done. And as I told you that I need to add actually A with minus B vector. So minus B vector is defined as the same vector as B of a same magnitude but opposite direction. That is what is being shown here. You could check that this is minus B. So again, as we know that the procedure as explained, if I try to join the tail of A to the head of the B, it represents the A minus B. So the D vector represents A minus B. Okay, so if you try to complete again parallelogram, you can also verify that that is D vector is same as minus B plus A. Okay. Yeah. So is that do you have any doubts with respect to addition and subtraction of the vector?
No, sir.
No, sir.
Okay. I'm getting response only from I hope Ankita and one more. What about others? Please, if you have any doubts, you are free to discuss.
No, sir.
May I know who is this?
Manas, sir.
Manas. Okay. Okay, yeah. So I'll proceed next. Multiplication of vector by a scalar. Okay, so okay, if we multiply a vector A by a scalar K, we obtain another vector B, such that I can write this B vector as K times A. Okay. So anyone could tell me what are the possible results for this? Is it a vector when you multiply a vector by back a scalar?
Yes, sir.
Yes, sir. Is it possible that we can make it as a scalar?
Yes, sir.
Yes. How?
By modulus.
By no, no. I mean, you are right. If I take as a modulus, then that is fine. But I'm asking, if you multiply a vector by a scalar quantity, what will be the result?
Vector.
Vector,
Vector.
sir.
Yes. I mean, we cannot
Vector.
really make them again back a scalar, right? Okay. Yeah. So now the magnitude of the B is, I mean, the magnitude of K and multiplied with the magnitude of A vector. Okay. So I hope this point is very clear. If K is greater than 0, that is, if it is positive, the direction of the B will be same as the direction of A. Am I right? And if K is less than 0, that is, if it is negative, the direction of B is opposite to the direction of the A. And also, if the magnitude of the K is greater than 1, the B vector will be longer than vector A. And if magnitude of K is less than 1, the B vector is shorter than A. I hope this point is clear, right?
Yes.
Yeah.
Yes, sir.
Okay. So next we'll go for now multiplication of vector, that is product of two vectors. And we say that there are two useful definitions for the product of two vectors. One of them is called as a dot product. It is also given by name as a scalar product, and other is referred to be other is referred as cross product, which is a vector product. Okay. So first we'll discuss about dot product, which is also, as I told you, it is also called as a scalar product. Now it is defined as product of the magnitude of two vectors. I mean, you should be very careful about this definition. It is defined as the product of the magnitude. It's a product of magnitude. Okay, of two vectors and the cosine of the smaller angle between them. Okay, and I define it as A dot B. Okay, the dot product is indicated as A dot B is equal to AB cos theta. That is product of magnitude of two vectors multiplied with the cos of angle between them, and it is a smaller angle between them. And graphically, I have shown here, if you have vector A and if you have a vector B, okay, and this angle represents a smaller angle between A and B. Okay, whereas this angle represents a larger angle. We should take a smaller angle between them. Okay. Now, what is very interesting about this particular thing is that, and you could see that this is a right angle triangle, and you could verify that this particular length is nothing but B cos theta. Okay, because cos theta is adjacent by hypotenuse, and you could see that if I take a cos theta equal to x divided by B, okay, and x equal to B cos theta, so you could check that this length, I mean the magnitude of this particular length will be B cos theta. Okay, so once it's clear with that, what we are saying is that the quantity B cos theta is said to be component of B along A and is commonly referred as scalar projection of B on A. So I'm trying to emphasize this point very often. These are very small things, but we'll be using very often as we proceed towards the Coulomb's law or electric field, the Gauss law or divergence and all. We'll often use unit vector, vector additions, and we may ask the question to us, we may ask a question that is, please find the component of P along A or projection of P along A. So if you have any doubt, please make it clear right now itself. So please remember, the quantity B cos theta is the component of B along A, and it is quite simple. You could see it's a projection of B on A, and more appropriately we say it as a scalar projection of B on A. Okay. Yeah. So now if you look to this mathematical definition of dot product, these points should be very clear. The first thing, dot product is scalar. Is it clear to everyone that dot product is scalar?
Yes,
Anyone
sir.
can justify why it is a scalar?
Yes, sir.
Yes.
Because it is the
Because I'm so
multiplication
correct.
of magnitude.
Yes. In this particular expression, we are seeing only the magnitudes or a scalar quantities. Is it? A is a scalar number. This is also just a number, and even this is also just a number. Is it? Yeah. And next we say that dot product is maximum when two vectors are parallel. Why it is so? Yes, anyone? Yes.
The cos 0 is 1, sir.
Yes, cos theta
Cos
is
0 is 1.
cos 0
1.
is 1.
Cos 0 is 1.
Yes, very good. Who is that?
Preeti, sir.
Huh?
Preeti.
Sorry, I'm not audible.
Preeti, sir.
Okay. She is correct. That is, when you say two vectors are parallel, the angle between them is 0. So cos 0 is 1, and this particular will be maximum. Okay. If dot product of two non-zero vectors, I have emphasized like non-zero vectors, is 0, then the two vectors are orthogonal. So can you justify why it is so? Anyone, please? If the dot product of two non-zero vector is 0, the two vectors are orthogonal. Anyone can justify, please, this? Yeah, please. I'm waiting. It would be better if it is interactive, or else I'm very sure that you will be an idle and doing your own work. Yes, Faizan. Yes, Vani. Are you there?
Yes, sir.
Yeah. It's quite simple. First of all, see, you can check out that this expression will go 0 when this angle is 90 degree. Yes or no? Cos 90 is what?
0.
0.
0.
0,
Is it?
sir.
Yeah, and what this theta represents? It's an angle between, a smaller angle between these two vectors, right? So it means that if this theta is 90 degree, it implies that these two vectors are perpendicular. Is that convincible?
Yes,
Yes,
sir.
sir.
Yeah, that's what we
Yes,
say.
yes.
If two vectors are perpendicular, the dot product is 0. Okay. Yeah. Okay. I continue. So next, the properties of dot product. It's very important. We say that the dot product is commutative. That is, A dot B is equal to B dot A. Next, we also say that a dot product is distributive over addition. That is A dot in bracket B plus C is equal to A dot B plus A dot C. Please try to remember this property in this way. First of all, it is commutative. The second thing is dot product is distributive over addition. Distributive means this A will distribute in this particular bracket. So that's why it is called as distributive law. So A dot distributes over addition. It is A dot B plus A dot C. Then scaling. If you scale A dot B, we can write this as K times A dot B, or first we can do A dot. First we can scale B and then you can perform the dot product. So please do remember this. This is also very important property. And next, A dot A is equal to A square. That is mod of A square. Okay. Why this is like this, we can prove it later. That is A dot A is A square. That is the square of magnitude. Okay. Okay, that's fine. So next, now we have a scalar projection. Okay. This B cos theta is called as scalar projection. Okay. It represents magnitude of this particular length. Okay. Now what I can do is, from equation 1, the scalar projection of B on A is, we know that it is a B cos theta. From equation 1, I can write this scalar projection quantity B cos theta as A dot B divided by A. Now what this A is?
Magnitude of A, vector A.
Yes, very good. The magnitude of A. Whether it's a scalar or a vector?
Scalar.
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 Okay. I can think this as 1 by A also, right? It's like simply a number as 1 by A. Is that? And you could see
Yes.
from a scaling property, I can say 1 by A as a K, 1 by A as K, and you could see by scaling property, I can write this as A divided by A dot B. That's what we have here. Vector A divided by A dot B. And what this quantity represents now?
Unit vector.
Yeah, unit
Unit
vector.
vector.
That is correct, unit vector. And I always prefer that you should specify it's along which vector. That makes complete sense.
Along A.
Yes,
Along
very good.
is
Yeah, this thing represents a unit vector along which vector?
vector A.
Vector A. So I can write this quantity as small a subscript A cap. That is unit vector along A dot B. And the same thing I can write it as B dot unit vector along A. So can you tell me why I can write like this?
Commutative law holds good for
Yes, very good. That's very good. Yeah, by commutative property, I can write like this. Okay. Is that clear now?
Yes, sir.
Yeah. So do remember the scalar projection of B on A is given by B dot A. B dot a unit vector along A. Okay. Yeah. So anyone could tell me what what will be the expression if I ask you? That is a scalar projection of A on B. Anyone, please? So now I hope it's clear. Now this B dot unit vector along A represents what? Scalar projection of which vector?
B, vector B on vector A.
Yes, very good. It's a scalar projection of B vector on A vector. So my question is, what would be the scalar projection of A vector on the B vector?
Vector A dot unit vector along B.
Unit vector of
Yes, very good. It will be a vector dot unit vector along.
Vector
B.
Vector
B.
Yes, very good. Is that is clear?
Yes, sir.
Yes, sir.
Yes, sir.
So you should remember this. We'll be often using this one. Okay, that's fine. Okay, so now we are clear about scalar projection of B on A, which is given as B cos theta, which is equal to B dot unit vector along A. So now can you think, now this is scalar, now you could see this is scalar quantity, number. Can I make it as a vector? Now this B cos theta or B dot unit vector along A represents magnitude. Now, can I specify this as a vector? You could see it's been written here by including unit vector along A in equation 2. We can define a vector projection of B on A as B cos theta multiplied with the unit vector along A. That is what is here. That's quite simple, right? Is that this point is clear?
Yes, sir.
Yeah, yeah. So it's quite simple. I'm trying to emphasize again and again. This B cos theta is nothing but it is trying to tell the magnitude of this line segment, which is being shown here. Okay. Now I want to represent this as a vector. It's quite simple. I'll try to identify what is the unit vector along this direction. And I know that this length is, or this direction is nothing but as same as direction of A. So simply I'll find what is the unit vector along A, and that I get multiplied over here. That is what I see. That's all. Okay, and you could see that even the equation 1 is also useful to determine an angle between two vectors A and B, that is cos theta is equal to A dot B divided by AB. Okay. Yeah. Yes. So before we go to the next point, so please, if you have any questions, you can ask. Yes. I'm asking repeatedly, is this point is convinced to everyone?
Yes, sir.
Yeah.
Yes, sir.
Yeah. So,
Yes, sir.
yeah. So can you
Yes,
tell me,
sir.
yeah. So can you tell me what is this part is? From this figure, what is that part is trying to tell us for this figure? Yes. Is that it is representing this length? Am I correct?
Yes.
Yes.
Yes, sir.
Yeah. Is it not? Because just now we, yeah, because just now we said that scalar projection of B on A is given as B dot unit vector along A. Okay. So when I say a scalar projection, it means it is telling only what magnitude of this particular line. Correct. So now I was interested to represent this line as a vector. As a vector. So quite simple. I saw that this line is nothing. I mean, this part of a line is along the A vector. So what I did is I tried to find what is a unit vector along this A, and this particular magnitude I multiplied with an a unit vector along it. And now you could see these two things represents a vector, that is this one. Okay. Okay, so I'll continue with the next, today's last topic, that is cross product. Okay, the cross product is a vector, okay, that is directed normal to the plane containing A and B. Okay, its magnitude is defined as product of vectors. Yeah, there is a small correction here actually. It's a product of magnitude of vectors. This should be, I can write this much. Yeah, it's a product of magnitude of vectors and sine of smaller angle between them. So magnitude of A cross B is given as AB into sine theta. Whereas we know that the cross product is a vector, and this actually represents a magnitude, and direction is given by A n hat. Now we should answer the question, what is A n hat? A n hat is unit vector normal to the plane containing A and B. Okay, because we said that the cross product is a vector that is directed normal to the plane, and hence A n hat represents a unit vector normal to the plane containing A and B, where this part is taken care by magnitude and this part is taking care of direction. Okay, so that is what is being shown here. If you have vector A and B which are in a one plane, and this vector vertical line which I'm trying to show represents A cross B. Okay, and the magnitude of this vector is given by AB sine theta, and direction is given by A n hat. Okay. Yeah. Now we have, right hand rule to find the direction of A cross B. That is, its direction is given by following the right hand rule. If fingers of right hand are curl in the sense necessary to rotate A through the smaller angle into coincide with B. That is, if you try to rotate A into B, and your thumb will point the direction of A cross B. The thumb points the direction of A cross B. Okay, so here we have some interesting fact that you could see now that A cross B is not equal to B cross A. That is, it is not commutative, whereas it is distributive over addition. That is, A cross in bracket B plus C is A cross B plus A cross, A cross C. It's distributive, and even the scaling is applicable over here. That is, first you can scale A and then you can do cross product, or you can first scale B and then you can do the cross product. Okay, so but the cross product is not distributive over you can say cross product. That is, it's not a distributive, it is associative. It is not associative. First first we can associative with, first we can perform B cross C and then we can perform A cross. We can perform A cross with this one, but it is not same as if you first perform A cross B and then you perform the result of this with a C1. Okay, this is important. It is not associative. Okay, and also A cross A is 0. So anyone can justify why it is 0? It's quite simple. You can just
Sine
yes, very good. Sine 0 is
0.
0. So A cross A is 0. Okay, so that's all for today's class. So if you have any doubts, please.
Sir,
Yes.
sir, A N hat you said no, sir. What is normal in that?
What is?
Normal, meaning of normal in that equation.
Yes, where?
In cross product, sir.
Oh yeah, in cross product. Normal means perpendicular.
Okay, sir.
Yeah. So if you take a plain book, yeah. So
Yes.
I hope you got that. If you take a plain book and if you keep a pen perpendicular to that, that itself is normal.
Hmm.
Yeah.
Yes, sir.
Yeah. I mean, like whenever you scale, whenever we say unit vector along that particular direction, we use normal rather than perpendicular. That's all. But it means perpendicular.
Yes, sir. Thank you, sir.
Yeah. Welcome. Any other questions, please? Yes? No?
No, sir.
Okay. If it's not
Sir.
that, yes, Hedri.
So what about 180 degrees, sir? 80 degree.
180 degree.
Yes, sir.
I didn't get the point. You are speaking with respect to which topic?
In dot product, sir, because in sine it is 0, sir.
Okay.
So in dot product, if we consider cos 180, it is opposite in the direction, no, sir.
Yes. Yeah, it will be, so cos 180 is -1. Yes.
So I mean the magnitude, like what about the magnitude of b cos theta in that case, sir?
What is magnitude? So magnitude will be only the, we have to ignore the sign of that one. We have to consider only AB.
Okay.
Yeah. Yes. Okay. If you have any more questions, we'll continue. Otherwise, one question for you people. Say, for example, I have here vector A, and I'm trying to okay, write it magnitude as 2. Okay, and this is okay. So now, can you can you tell me that is how we can write this particular as a vector? That is as a vector. How we can write this?
2 by magnitude of A.
Yes.
2 I cap.
2?
I cap.
No. See, right now we are in the graphical representation, right? Till we have not moved to this particular, what we say is any coordinate system. So we'll not speak in terms of I, J, K.
Into cos.
You try to
2
write,
into magnitude of a, sir.
no, 2 itself represents magnitude of A. That is correct, 2.
Into cos theta.
No.
cap. A cap.
Yeah, something, you are right. What I should write here?
Unit vector.
A?
Unit vector.
A cap.
Yeah, that is A cap, and subscript is what?
A.
Yeah.
Yes,
Yes.
sir.
Yeah. Is that is clear?
Yes, sir.
Yes,
Yeah.
sir.
Exactly. Okay. Yeah. Yeah. One more thing. Yeah. So if I give one more vector here as C vector, So can you tell me what is a unit vector along this? Or what's unit vector?
A cap along C.
A cap
Subscript C.
subscript C is
C.
equal to
C
is equal
vector divided C
is
vector
a
C vector C divided by by modulus of C.
by magnitude of
C. Vector C.
magnitude of C. Is that?
Yes, sir.
Yes, that is correct.
Yes, sir.
Okay. Yes, that's fine. So this is was an important point. What I was trying to, I mean, that is what I was trying to get from you, and that is what the same thing is being written here. Okay. Yeah, and that is same thing is also used in the dot product. I was trying to use often. That is what this one. So this is representing magnitude, and this is representing direction. Okay, so if you have any doubts so far, is that is clear?
Yes, sir.
Yes, sir. Yes,
Yes,
sir.
sir.
Okay, that's fine. So we'll stop here session. We'll stop the session here. So thank you for joining.
Thank you, sir.
So just a minute. I'll try to download the attendance, and then after you can leave. Okay, that's fine. Thank you.
Thank you, sir.